Good afternoon, everyone. This is Sam Cluse from the NAIC. Welcome to the October Book Club call. This is a Casualty Actuarial and Statistical Task Force open call. We do not do a roll call for these calls. We are recording this meeting today. We will be muting all attendees upon entry to cut down on background noise, but please hold on to your questions until the end of the presentations, and then you can feel free to unmute yourself. You can also enter questions into the chat. Our speakers today are Dorothy Andrews, Roberto Perez, and myself from the NAIC Model Review Team. Our focus is helping state regulators keep up with the evolving modeling methods used by insurance companies. I'm now going to turn over the meeting to our first speaker. Go ahead, Dorothy.
Thank you, Sam. So we're going to talk about p-values and some alternatives to p-values because unlike GLMs and other regression type models, not every model has a p-value. So it's important to understand how to interpret the results when you don't have really clean p-values. There may be different ways to go about getting a p-value for a model rather than some of the standard ones. But I'm going to talk about some of the standard ones first. And then Sam and Roberto will talk about some of the non-standard ones, ways of going about getting a p-value and for different types of models. Okay. So, what's often lost when we do regression models, generalized linear models, is that there are actually two tests of hypotheses that we are testing when we run those, and it's not often talked about. So the first test of hypothesis is whether your beta values or your parameter estimates are going to be zero. And that's the p-values have to be associated with a test. And then the second test of hypothesis is, are your variances equal? So typically we're looking at variances within groups and variances between groups. So we want to look at the ratio of those two, and that's often what we see as the F test in our regression output. And that tells us that we're asking the question, is the variance that's being explained by the model greater than the variance, that the residual variance that's left over? So the F test is a ratio of variance test. And so when we do a GLM or a regression model, we're actually testing those two tests of hypothesis. And then we have to figure out, when we get a test statistic, is it actually statistically significant? So what you see here is, it looks like the normal distribution. And so many textbooks refer to it as the Gaussian curve, reflecting the fact that the 19th century German mathematician Carl Friedrich Gauss deduced the shape of the curve while he was studying how data are affected by random errors. But then we also had Abraham de Moivre, who arrived at the same curve decades earlier while tackling a problem that had baffled mathematicians for many years. And that is how to calculate the frequency that the heads or tails appear over the course of many coin tosses. So today, this curve is referred to as either the Gaussian curve, and we also call it the normal curve. Even though history is there's some conflict, depends on what history book you're reading as to who really invented the normal curve. But as you can see in the diagram, when we talk about a p-value is not a single point on the curve. It refers to an area under the curve. And if we look at what's being referred to as this observed point, and we drop a vertical through that observed point, we want to look at how much area gets cut off to the left of that point in this case. And that whole area represents the p-value, because we're trying to understand how likely it is that we got that value, that numerical value of that statistic by chance. And so that whole area represents the p-value, and it's not just a point on the curve. So the other thing about distributions and curves is that their shape, unlike the normal curve, which isn't affected by how much data you have. It's affected by it has scale and shape parameters, but other distributions are also affected by what we call degrees of freedom, and that's basically refers to how much data you have because you have these distributions. I don't know if you're familiar with sampling distributions, but um, depending on how much data you have, if you resample the data over and over and you're creating a particular test statistic, you want to look at how probable, look at the distribution of that test statistic across all those subsamples or that you pull from that population. Well, there are three main distributions that are really dependent on degrees of freedom to determine their shape. And they are the chi-square distribution, and this usually involves tests of hypothesis involving count data. We have the Fisher's F distribution, and the Fisher F distribution was named after Ronald A. Fisher. A lot of statisticians like to name things after themselves, and that's why it's called the F distribution. And we have the student T's distribution, and the student T's distribution is actually, I forget the guy's name, but he worked for a beer company, and his company didn't allow him to publish things under his own name. So he called the distribution he developed the student T's distribution. But for each one of these distributions, and we're going to look at it, the shape of the distribution is determined by how many degrees of freedom. And given a different shape based off the degrees of freedom, the amount of area to the right of a given test statistic, that shaded area, that red area that we saw under the normal, will look different. So as an example, let's take a look at the chi-square. We have three distributions of chi-squares here based off of, and there's actually three more on the next slide. But you can see for a chi-square with a distribution, a degree of freedom of 1, it has this kind of shape. And then as the degrees of freedom increase, the shape of its changes. So, and what happens is you can see the area gets put, more and more area gets pushed off to the right. And as a result, we can see that the probability that you would get a value that's greater than 4 also starts to increase. So we can see if those represented p-values, those areas represented p-values, we can see how the p-values would be affected by each one of these distributions. And we would need a much larger test statistic in order to have something that is statistically significant by some benchmark, usually what we call 0.05. We take that as a benchmark, although it was arbitrarily set as a way of, as a nice compromise in determining the power of a test. So there's a lot of history on why 0.05 is used so much in statistical analysis and hypothesis testing, but we'll say that for another day. So you can see as we go from degree of freedom equal to 1, the probability that something is greater, that x is greater than 4 is 0.055. For degree of freedom 2, it hops up quite a bit to 0.13. And for degree of freedom 4, it really jumps up to 0.406. And if we go to a distribution with a degree of freedom of 8, we get to 0.85. So on this distribution, to get something that's statistically significant, your value would have to probably be much greater than 20 in order to get it then on 0.05 threshold. And for 10, we're really close to 1. And then for with 16 degrees of freedom, and then with degrees of freedom of 32, we're super, super close to 1. So, and this type of, we see these changes in the probabilities for the other distributions as well. We're not going to walk through in detail what the other distributions look like for a specific value, but you can kind of imagine in your mind that when we look at the F distribution, you can see the black line is for an F distribution where it has 2 degrees of freedom. So because the F ratio is the ratio of 2 variances, the numerator has a degree of freedom, and so does the denominator. So the first degree of freedom represents the numerator degrees of freedom, and the second represents the denominator degrees of freedom. And so Fisher came up with these tables, just by running experiments over and over, doing a lot of, creating a lot of sampling distributions to arrive at the tables that are usually in the back of statistical textbooks. I don't think they are anymore, but when I went to school, they were in the back of statistical textbooks. But you can see as the degrees of freedom change, the shape of the distribution changes. And that means as the shape starts to move from the left to the right, more area gets pushed off to the right. And that means you need a much greater test to statistic value in order to reach statistical significance. I'm getting a little tongue-tied here, sorry. So that's how the F distribution looks. The T distribution approaches a normal distribution, but again, it has the same patterns. When you have when the degrees of freedom is equal to 1, you get this nice purple curve that's kind of has a lot of area in the tails, has fat tails. But as you increase the number of degrees of freedom, you can see that this particular distribution moves closer and closer to the standard normal distribution. And so again, you need bigger and bigger values. In this case, you need, you get more area. You need smaller values will give you a greater statistical significance than with a degree of freedom 1. You need to go out further on the curve. So one of the things about p-values, because we often put a lot of emphasis on p-values, and sometimes too much emphasis because, p-values are subject to a lot of manipulation. So the American Statistical Association came out with a paper, and you can find this paper online, talking about warning people about placing too much confidence in p-values. And so, as well as, things to be aware of with regard to p-values. So one is that, the one thing it can tell you is like how incompatible your data is with your statistical hypothesis. And we talk about p-hacking, you can see people will take their data, will do a lot of things to the data, massage it in ways in order to get a significant p-value. But the raw data itself, the p-value may be telling you that there's something incompatible with your between your data and your statistical hypothesis. Another thing is some people think that the p-value is measuring the probability that the hypothesis is true, which is also false. The p-value is simply telling you how likely it is that you got this test statistic that you did by chance. It is just a measure of all the area to the right of that test statistic on your distribution. And if you have a two-tailed test, it's really towards the extremes, how much area you push off to the extremes. Oftentimes, if we talk about a one-tailed test, that p-value is to the right, but you can split your p-values between the two tails of your distribution. And we're really talking about the values on the outside of those test statistics. And it said, so again, when we look at model output, the ASA warns that you shouldn't base your decisions solely on p-values. And one of the things that is true, if you look at a lot of statistical tests, people who invented these different tests didn't necessarily consult each other to make sure that each statistical test was compatible with one another. So oftentimes you can get a situation where two tests on the same data will give you conflicting results. One will be statistically significant and the other test will be insignificant. And so then the question is, what do you do? Well, that becomes, a huge topic of discussion for the modelers. You want to definitely provide full transparency. You want to set your p-value at the beginning of the experiment, and you should not be changing your p-value once you look at your results, because that's cheating. The p-value also does not measure the size of an effect or how important the result is. The p-value is simply a measure of how probable it is that you got the test statistic that you got based off of your data by chance, and that's it. And so we have to make sure that, you know, if to look at other measures in combination with p-values, because again, there are a lot of conflicting, um, there can be a lot of conflicts between what a p-value tells you and what some of the other tests tell you. So the ASA really felt that it was important to put out that statement, you know, for all of professionals to understand. So there is a nice connection between confidence intervals and p-values that we'll talk about. I found this graphic I thought was really cute, because it did involve a box plot and an outlier. And as this comic says, she's feels she's very significant, but she's more significant than the others because she is the outlier. Now, in romance, outliers might be a good thing, but in modeling, we know that outliers can be problematic. So when looking at the relationship between these two, you can take this interval between your lower confidence limit and your upper confidence limit and see where it fits on the distribution. And so basically, the between your lower limit and your upper limit, you're trying to say that you're 95% confident that your uh, point that the true value lies within that that limit. Um, so uh, so you can see here is where on the left side you can see where there is a distribution cutoff, and that's a critical value. So if you get a test statistic that's smaller than a negative 1.96, it would be significant on that end. And if it's greater than 1.96, you would say that it's also statistically significant. And we have to divide the alpha, the p-value that we set at the beginning of the experiment, divided by 2 if we have a two-tailed test. If it's a one-tailed test, it can be either an upper tail or a lower tail, and we find the critical value where all the area is in either the upper tail or the lower tail, and our test statistic has to exceed one of those points in order to be statistically significant. So another way of thinking about a confidence interval um, is if you take random draws from a population multiple times, then you would expect for the true value to lie in those intervals 95% of the time. So in this graphic, this is showing that if we took 100 samples with n equal 3 and a mean equals 10, and we calculated the mean for each one of those samples, and then calculated the confidence interval for each one of those samples, we would expect 95 of them to contain the true mean. And this red line is representing the true mean. And so clearly for any given sample, the means could be different, but we expect the true mean to lie in one of those intervals. And if you look at this graph, you can see we have 5 intervals that do not contain the true mean. So the last thing I wanted to talk about is p-hacking, because p-hacking is technically cheating when you're doing any kind of statistical analysis. If your statistical analysis, if you are doing it with a high degree of ethics, you set your p-value at the beginning, you run your experiment, you create your test statistic, and you compare it to the critical value associated with the p-value you set at the beginning of the experiment. If your p-value, your test statistic is greater than that critical value and absolute value, you say that your test statistic is statistically significant, that you would accept your, you reject your null hypothesis is the way it would work. In which case, we see this all the time. We don't actually think about this very in these formal terms with respect to when we look at output from statistical results, it kind of disappears. But this is really what's going on. We are testing hypotheses with these models, and p-values are associated with tests of hypotheses. So p-hacking, that's a term that came into use as psychology and other fields of science were experiencing a kind of existential crisis. They were finding that their findings wouldn't replicate. They were getting absurd results, and they couldn't get past peer review and well-respected journals. And so they were trying to find ways to test for, false positives and find results that, would look good. And so they began to realize that some of the problem might be, part of ingrained in some of the basic research practices. So when we look at p-hacking, you may not get a statistically significant result. And then people say, well, let me go back to the drawing board and see, what if I change, tweak some of my test parameters? What if I collect some more data? What if I do some transformations to the data? Make some adjustments, or not adjust for multiple comparisons. You can omit outliers, and we see this all the time with capping. We can analyze subsets. We can make changes to the underlying data so that we end up getting something that's statistically significant. Or you could change the response variable. You see people do that as well. Or you could use a different test. Like I said earlier, a lot of these statistical tests don't necessarily weren't necessarily designed to make sure that they were consistent with each other. So you will find some tests will give you a statistically significant result, whereas other tests may not. So while p-hacking, we understand what it is and how it can happen. The truth is, in the work that we do, reviewing models by other companies, there's no way we would be able to determine whether someone engaged in p-hacking unless we were actually on the modeling team, because we only see like the end result. But it is something to be aware of and understand. So now I will turn it over to Roberto.
Thank you, Dorothy. So I'll be talking about availability in packages, but I'll also be talking about methods that don't produce p-values as well. So if you go to the next slide, before I get into the meat of my part of the presentation, I wanted to just talk a little bit more about p-hacking, just to further illustrate the point Dorothy was making. So I found this little graphic here, and to summarize what's happening, just think about people trying to find a relationship between eating jelly beans and acne. And they go to some scientists and they ask them to perform an experiment to see if there's a relationship, and the scientists do this for a threshold value p equals 0.05, so a 95% confidence. And they do the analysis, they come back and they say, we found no relationship between jelly beans and acne. Okay, so that should be it, but no, then the people ask the scientists again, oh, I think it's just a specific color of jelly beans. Can you do this experiment again? And then the scientists say, yeah, I'll do it. They do it for brown jelly beans, and they come back and they say, whoop, nope, no relationship. And then same thing again, say, oh, try it for blue. Same thing, no relationship, and so on. And they keep doing this for every color they can think of. And eventually, when the scientists test the green jelly beans, they find a statistically significant relationship between green jelly beans and acne. Now, the question is, should the journalists or people asking the scientists this then go and publish an article on a newspaper or journal saying green jelly beans are statistically correlated with acne? And the answer is that they shouldn't do that. And that's because the scientists found that correlation just by random chance. If you test enough colors, even if there's no correlation, just by random chance, it is likely that out of 20 colors that you test, one is going to show significance. I just wanted to show this to kind of illustrate and show an example of a way p-hacking can show up. This is also analogous, kind of going on a tangent to our presentation, more to our work on the model review team. This is analogous to what could happen when a company doesn't use a true holdout or testing dataset, and they only use their training dataset to iterate and select variables based on their results. And this also happens even if they're subdividing that training dataset into a validation. If the validation dataset is being used to test, as is shown in this graphic here, eventually you may end up with something significant just by random chance. So it is important to keep that in mind. And like Dorothy said, that's something that's hard to determine if it's happening unless you're in the modeling team. But we can take precautions about it, right? So requesting data on true unseen data, requesting results on true unseen data is something we can do to test if the model results are actually significant and it's not something that just happened by random chance. So next slide. And having gone through that, so let's get to the. I just wanted to show that, but let's get to the bulk of my part of the presentation, which is about methods that don't produce p-values and their availability. So first, I wanted to go back to the basics and give a brief overview of what traditional regression is. In traditional regression, we usually want to estimate the coefficients or betas that when multiplied by our explanatory variables or the x's, better predict our target or y's. And we can see this in the formula that I have here on the center left of the slide. Y equals a function of x and betas, which in the traditional regression case is a sum product x1 times beta 1 plus x2 times beta 2, etc., plus an intercept plus an error term. So in order to determine these betas, we can set up a loss function that's basically the squared error, the actuals minus the predictions of the model. And by minimizing this, by selecting the set of betas that minimize this function, we can get that set of betas that better models our data. So you can see on the graph to the right, it is analogous to adjusting this linear line so that it better fits our data points. A very important property of these beta coefficients that we estimate in this way is that they are unbiased. And this allows us to obtain p-values and confidence intervals around them, just as Dorothy was discussing. If we go to the next slide. So having gone through what traditional regression is, now I want to introduce the concept of penalized regression. And this was introduced by Zhu and Hasty in 2005. And you may or may not recognize Trevor Hasty, also as one of the authors of the famous Introduction to Statistical Learning and Elements of Statistical Learning books. So penalized regressions are very similar to traditional regression, as I showed before. But the difference is that we are adding a few more constraints to the loss function we're using to estimate this beta coefficients. So on the formula to the left, you can see how this looks like for the general span of penalized regression families. If we go to the next slide, we're going to look at this function into a little more detail. So again, if we isolate into this part of the equation and we remove the next two terms, we are left with just traditional regression. If we minimize that square error, we're gonna left with the betas obtained through traditional regression. Now, if we go to the next slide, we'll see that if we take that square error term and we then add another term composed of a constant lambda times the L2 norm, and this second part here is known as the L2 norm, and that is the square root of the sum of squares of the beta coefficients. If we take those two terms and we minimize that function instead of just the square error, we're left with what is known as rich regression. And note that this is essentially a way of penalizing bigger coefficients. We are minimizing the same formula on the left as traditional regression, but we're adding this additional term that's going to penalize bigger coefficients. We can think about this as adding bias to our estimates of the beta coefficients. And that lambda parameter is also known as the penalization parameter, which is going to control how much we penalize bigger coefficients. If lambda is a bigger value, then that's going to add a bigger penalty to higher values of the betas. If lambda is smaller, then the penalty is smaller as well. The graph at the bottom here illustrates what happens to the coefficients under rich regression as we vary that lambda parameter. So lambda will be on the x-axis here, and we can see if we go to the extreme right, that'll be where lambda equals 0. In which case, this becomes traditional regression. As lambda becomes bigger, we increase that penalty. The estimates of the coefficients that we're going to get trend towards 0, shrink towards 0 because they're being penalized. If we go to the next slide, so if instead of doing using the L2 norm, we add the L1 norm, and remember L2 was the square root of the squares of the betas. The L1 norm is the sum of the absolute values. If we instead define the loss function as the square errors plus the lambda times the L1 norm, then we obtain what's known as lasso regression. And note that this is also a way of penalizing bigger coefficients, just in a different manner. Contrary to rich regression, when we use lasso regression, we perform lasso regression, and we have a big enough value of lambda, the penalization parameter, some coefficients actually shrink to 0. Whereas in rich, they'll go to 0, but they'll never truly become 0. In lasso regression, if lambda is big enough, some parameters will become actually 0, and they'll be essentially removed from the regression form. And the graph below illustrates how this looks like. So this is analogous to what we show for rich regression. You can see if we go to the absolute right, where lambda equals 0, we're left with traditional regression. As we increase lambda to the left, in this case, some coefficients actually become 0 and get fully removed from the regression equation. So in a way, we can think of lasso also as a variable selection methodology. Now, we don't have to do only lasso or only rich. Sometimes we can combine both penalties and use both L1 and L2 penalties. And when we do that, that's known as an elastic net regression. And usually the way that is done is by adding another parameter alpha that's going to control how much we're going to use each one of the L1, L2 norms. And it usually looks like this. So we should take a look at the lambda 2. Sorry, let's go back to the same slide. If we take a look at the first term, lambda 2, the L2 norm, we multiply that by alpha, and then the last term we multiply by 1 minus alpha, and then we vary alpha from 0 to 1. So we get the whole span of combinations of the two methods. So I just wanted to give that introduction to what we mean when we talk about penalized regression. If we go to the next slide, so if we use penalized regression in R or Python, the vast majority of packages will not provide p-values as they would for a traditional regression methodology. And to quote the authors of the penalized R package, which is a package we can use to fit these models, Standard errors are not very meaningful for strongly biased estimates, such as those that arise from penalized estimation methods. And as we mentioned before, penalized methods introduce bias when we're estimating the beta coefficient, which then becomes a big component of MSE, mean square error, which if we recall is bias squared plus variance. And because of this, if we produce confidence intervals based on variance, they can be misleading for these methods. If we go to the next slide, here I show other R packages that we can use to fit penalized regression methods. Like I mentioned, penalize is one. There's also GLMNet, which I believe is the most widely used package in R for this method. But we can also use packages such as HDM, Big Lasso, Caret, H2O, etc. And Python also has several libraries that we can use for these purposes, sklearn. There's another one I believe called Lasso, etc. However, there's one package in R that does produce p-values, and that is Lasso PV. And the way that this package produces p-values is by looking at the regularization strength when each predictor enters um, the regularization path. And the regularization path is what we showed before of the lambda on the x-axis graph, where we see, for example, for lasso, where if lambda gets big enough, some parameters, some variables go to zero, some coefficients for some variables go to zero, and they get removed from the regression equation. So what this package does is that it operates under the assumption that coefficients that go to zero first are less important, and that's how this determines the p-values for lasso. Now this is an alternative, but it's important to note that it's a different methodology of determining them. So if we go to the next slide, I also want to talk about generalized additive models. So this is another method for which we need to be careful when we are evaluating the p-values that are output by the method or package or formula. And this, in the same way as penalized regression methods, are another variation of traditional GLMs. So for the case of generalized additive models, we use a smooth function of the predictors instead of assuming that the target variable is modeled through linear functions. So we can see an example of how this will look like on the function on the top of the slide. And the NAIC model review team has had presentations on generalized additive models before. The email that was included for this meeting invite has a link to all our prior presentations that you can reference if you want to learn more about GAMs or generalized additive models. So anyway, when we're thinking about p-values for GAMs, especially for those smooth functions, it's important to know that for GAMs we can have the smooth functions, but we can also have the more traditional fixed effects. So when we're looking at p-values for smooth functions, we set the null hypothesis as the smooth function equals to 0. And in R, we can use the MGCV package to fit these models. And they produce p-values, but also specify that these p-values are just approximations, since they are computed without considering the uncertainty in the smoothing parameter estimates. For example, if there's a lot of uncertainty in the smoothing parameters used to determine the smooth functions, then the p-values are likely to be underestimated. And it's important to keep this in mind when evaluating the output of these kinds of models. And Sam, after this, will talk more about alternatives that we can use to better understand the outputs of these models, especially when the methods don't produce p-values by themselves. So that's it. So I'll just pass it along to Sam to continue on that alternatives of p-values.
Right. Thanks, Roberto. For my section, I'll start by reiterating the importance of, we still want to look at things by variable. So what can you do when you want to check the significance of each variable, but the model doesn't provide p-values? So That's what we're going to get into. And my section has several exhibits and plots that were built with the use of R. And I wanted to give a special thanks to our actuarial intern Jackson Crowther. He helped us write the R code for that. That was a project we did together. So we were co-authors on that. If we could move to the next slide. So occasionally, companies will reply to us when we're asking about a specific variable, and they'll talk about, well, the overall model generalizes well to new data, and they'll also refer us to the exhibit with a lift chart. And one thing I wanted to point out is that a lift chart, even on holdout data, may not look that bad if there's one or two insignificant variables included in the model. And we did sort of an experiment to prove this point. If you could go to the next slide. So the first thing we did, and this slide is all about, we'll use GLMs, and after that we'll transition to talking about elastic net models. But for the experiment we did, we took a data set that's from the CAS datasets package. We built a GLM using the data in the package, but then we also added 100 columns that had random numbers in it. Each of those 100 columns is just filled with random numbers between 1 and 5. And then when we did that and looked at the p-values that came out of that, 7 of the 100 columns came back with a p-value that was less than 0.05, which is close to the 5% that you would expect to see randomly. So then I wanted to do a comparison. Look at a lift chart where I built a model using the real predictive variables and including the random columns, and then one that included and then one including just the regular predictor variables. So if you're looking at the plot on the top right, that's what you get if you're building a model that has none of the random columns in it. And then if you're looking at the bottom right plot, that's what you get when you're building a model that includes the same variables plus 2 random columns. And if you were actually to see both of these, you might say that the top plot is better. The observed averages are much closer to the fitted averages. But if you were only to be provided the bottom right plot, which includes the random variables, it would be hard to disagree with that plot, even though we know based on the experiment we put together, we know ahead of time that this includes some variables in it that are based on random data. So I think it's useful to see lift charts, but we also want to see some information by variable still. But what can you do if the modeling type that's used does not offer p-values? Let's go to the next slide. If p-values are not available, there are other tests that may help you address the question of significance on a variable by variable basis. One thing you could look at is bootstrapping, and then look at, do the variations to the data result in radically different coefficients? You could also, if a company is using cross-fold validation, are the coefficients that are coming out of the model, are they consistent across folds? And lastly, if it's a penalized regression model, you could build a GLM reference model and then take a look, well, what are the p-values from a similar GLM? And I'm going to dive into each of these in the following slides. So for bootstrapping, a model could be run several times on bootstrap samples. And bootstrapping involves sampling with replacement from the original data set. And then you end up with different data sets, each of them having the same number of records. Maybe your original data set has 100,000 records. Each of your bootstrap samples is also going to have 100,000 records. And then you run a model on all of those different bootstrap samples, and you're going to get different coefficients because the data set underlying each one is different. And then you could look at evaluating the coefficients. You can look at the range of coefficients. Is there a large range or a small range? If the range is narrow, that raises our confidence that in statistical significance. If the range is quite wide, that could be a sign of model instability. And histograms can help you visualize this range and the distribution of coefficients. And generally, narrower histograms with tall peaks, those are preferable. And then if you have a variable where the histogram crosses over the zero line, that should be further scrutinized. If you could go to the next slide, we show the results from an example we did. We built an elastic net model, and it didn't provide p-values. So what we did was we ran the elastic net model on 1,000 bootstrap data samples to look at what are the range of coefficients you get out of it. And then, so looking at these plots to the right, I'll describe what they mean. So the dashed blue vertical line, that's the coefficient you would get when you run it on the full data set, the full original data set. And then the histogram is showing you how many times you get different coefficients from the bootstrap data set. So you can see the count of the models is what's being measured by the y-axis. And so you can see sort of the range you're getting from the different variables. And then the red line, that's a reference line just at 0. These were log-link models. So I'm looking to see, are there examples where that actually crosses the 0 line? And in this one, the example, the bottom left plot, the female coefficient, you can see it's got a fairly wide range of coefficients, and then some of them actually cross over the 0 line, which means you're less sure of whether it should be a surcharge versus a discount in that case. We can move on to the next slide. So another thing you could look at would be cross-fold validation. K-fold validation is a common cross-fold validation type. And in this case, the training data, you break it up into 5 folds. And then ideally, the modeler still has a separate true holdout data set for final model validation. So looking at the diagram to the right. So if we look at the line that starts with split 1. So in the first split, you're training on, you're generating predictions for fold 1, and you're doing that by training with folds 2, 3, 4, and 5. And then you're taking a second split, and that would be making predictions on fold 2, but your training data includes fold 1, 3, 4, and 5. So you can see ultimately you have K different models as well. Go on to the next slide. So your model ends up being trained K times when you do this. And the predictions for each fold are based on a model trained with all the other folds. And each time the model is trained, a set of coefficients is determined. And depending on what package you're using, the modeler may need to specify that they want each of these, each fold's coefficients to be saved. Go to the next slide. So often the final model is run using 100% of the training data, including all folds. And companies often are just providing the coefficients that are associated with the final run. Okay, and then if you go to the next slide, we have an example. Oh. Okay, one more slide. The model reviewer can ask for coefficients from each fold. And then in this example, we built an elastic net model, and then we did essentially 5-fold training. And we looked at the coefficients from each of the folds. That's the numbers 1 through 5 there. And then we also have the coefficients from the full data set. So you can look at this and you can get an idea of the range of possible coefficient values. Okay, we have a couple questions. One is for large data sets, bootstrapping seems time and resource intensive. Um, is this something reasonable to request that the insurer provide? So it is definitely the most time intensive, and it also varies a lot based on the size of the data set. So I would keep that in mind. I have a comparison of the different alternatives coming up, and then to the next question. When I was doing these iterations of bootstrapping and also for the cross-fold validation, I was using the same predictors each time. Go to the next slide. The last potential idea is looking at GLM reference model. So GLMs, they provide p-values in most software. And a GLM could be built which is as similar as possible to the model in question. This is probably more appropriate when the model in question is still some type of linear model. So one of the penalized regressions that Roberto talked about earlier, like lasso, ridge, or elastic net. Most of my examples have been elastic net. And you could consider the GLM provided p-values as sort of a close approximation for the model in question, although they may be a little underestimated. And also, one thing we recommend is asking a company to describe why their model type is preferable to a GLM for their modeling purpose. So if you do this exercise of building a GLM for reference model, you now have a non-GLM model and a GLM model, and you should talk about why they favor the non-GLM model. There are some people who say, you can use the lasso model or elastic net model for variable selection, but why not run a GLM on the final features? Why is it important to constrain the model? So that's something you could ask, and GLMs provide those useful model diagnostics. And also another caveat, if the coefficients are radically different in the reference model from the model in question, then the GLM p-values may not be as relevant. Next slide. So in this case, I built a elastic net model, and then we built a GLM model with the same variables. And then you can compare the coefficients side by side to see if they're reasonably close and look at what the p-values from the reference GLM are. And low p-values from the GLM suggest the variable should be more significant. So if you do a comparison here, you'll see the elastic net variables are pretty close to the reference GLM. They're constrained so that they're a little bit closer to 0 than the reference GLM coefficients, but in this case they're pretty close, and you may find that those p-values are informative. I also wanted to mention that these are all things that we've seen companies used in filings, and they seemed pretty compelling. And going back to the question about bootstrapping, we have seen that provided in a filing before, although it does depend on the size of the data set. If we could go to the next slide. So sort of comparing the different alternatives that I've talked about today, bootstrapping can provide a large distribution of coefficients, but it might be impractical for large data sets due to the model runtime. For k-fold validation, that provides a much smaller distribution of coefficients, and it may require the modeler to change some of the programming in order to save coefficients from each fold. And it takes less time than the bootstrapping approach since there are less model runs. And also, finally, for a GLM reference model, that would not be appropriate for a nonlinear model. And the p-values may not be as relevant if the beta coefficients are radically different from the model in question. But we've had questions before from regulators about what to do when there's a model type that doesn't provide p-values. And these are some of the things that we offer up as things you could ask for that may be helpful in evaluating a model. And I believe that's the end of our presentation, so we can open it up for questions. We have one question about k-fold validation. What coefficients are close enough to accept the variable in the model? And I don't know if I have an exact answer for that, but I think that might require some judgment. But at the same point, I think one of the main things you're looking for is if it includes both positive and negative numbers. If the range crosses the 0 line, it's important to see, oh, well, in some folds, this was considered a discount. In some folds, this was considered a surcharge. I think that would be something that I would look at. Um, Dorothy or Roberto, do you have thoughts on that? I think you're muted, Roberto.
Yes, I was muted. No, I was just saying I agree with you. That's subjective, but I think what you said is probably the main thing. The main first thing we should look at is whether it indicates discounts, surcharges, and different folds. If it does, then that means we're really not confident about what the models are indicating. But yeah, it's more of one of those things where there's some clear red flags that we can see when that is performed. So we kind of look for those to make sure.
Yeah, I was going to say the same thing.
I have a question for you. I guess my question is really what would cause the errors in the first place? And what I'm getting at is, are you expecting to find technical errors on the part of the insurer? Are you expecting to find intentional manipulation to get a particular desired outcome? You know, I typically would start from the assumption that insurers are doing the best modeling work they can, and they're incentivized to get costs to line up as closely as possible with reality. So, what are we expecting to come out of this if there is a problem? And, sort of, I guess, fundamentally, I'm getting at how important is it to scrutinize this sort of thing, given that it seems to me that most of the time the incentives are properly aligned in the first place for insurers to do the work correctly.
Um, I'll, I'll start with one of my concerns. One of my concerns is just with the advent of big data and a lot of people using big data, third-party data. Maybe they pull in an extra like 200, 300 variables that they didn't used to before. Um, kind of as we talked about before, some of those may appear to be predictive by chance, and we want to sort of weed that out. And some people, you know, I don't. Yeah, I worry about people like they spend a lot of money in order to get external data. They feel like they have to use it. There might be an issue like that. We just want to make sure that there aren't like spurious correlations in the data, things that are just happening by chance. That's something that comes to mind. One of the reasons we still look at it, look at justification by variable. Then Roberto or Dorothy, you want to add to that?
Yeah, so I'll add that, modeling is, we often say that modeling is an art. So there is a lot of activity around like model selection, how much data you should use. So are these things considered p hacking, or is that just part of normal model development? I get concerned when, like Sam said, you have a lot of this third-party data that's coming into modeling, and some of that third-party data, has, a dirty history. It might be historically tied to, racially biased or impacts on people, or other kinds of biased impacts on people. So, I think just looking for statistical significance really is not enough. I mean, we really need to understand like how this data this third party data in particular was developed. Does it have a history of discrimination associated with it? And if it's included in models, how is that history of discrimination going to uh, influence the outcomes of the variables of the model? So those would be some of the concerns I have. But yeah, p hacking can look like model development too. So um, it's hard to decide what to tell what someone's intention is. Like, we don't know if they got a bad result, and they probably did get a bad result, right? So the first time you create a model, you have some data elements in there. You might not have the right interaction terms. You might need some other terms in there. So all of this is part of data development, but there should be some integrity between like what it is you're trying to test, and not changing the design of your experiment to meet the outcomes that you received. So there should be more research integrity and development of these models.
I think you both covered it very well. I just wanted to add another example is, and I do agree that in theory, companies should have their priorities should align with what we want to look for. But sometimes there's preconceived notions about certain variables. So the companies may have a good intention, but the data doesn't support it. So something like p hacking could fit into that, kind of to support preconceived notions where it really shouldn't be. So I just wanted to add that there, but I think my Dorothy and Sam covered it very well.
Looks like there's another comment, Sam.
I think it's a related comment that the incentive would be optimization, that companies have an incentive to optimize their models and not include insignificant variables. But I think that brings us to the end of our time. Feel free to reach out to our team if you have any more questions or want to make any more comments. But I'd like to thank everyone for attending today and listening to our conversation. And I'll see you all at the next book club recording.